Have you ever wondered what sets human beings as a species separate from the rest? We know that we are not the toughest, we are not the strongest, we are not the fastest. We don't see better than every other animal, we don't smell better than every other animal. We can't hear better than some of the other animals. But what sets us apart from the rest is we have a brain which makes us capable of doing things and thinking things out so as to perform at a much different level. If you observe, the lions which lived in caves for thousands of years have continued to stay in the same caves. I mean, we are not talking about those lions which we got into the zoo, but the regular lions in the forest, the regular elephants in the forest, they stay in their own environment without making much changes. The birds continue to stay in the nest, the monkeys on the trees. Of course, the environmentalists probably will find that that's a better way to live. But as human beings, in over last 10 to 12,000 years, we have moved out of the caves, gotten into multi-storied buildings. We learned how to communicate in the quickest way, both using physical vehicles or through the communication channels. What makes it different for us is we are capable of thinking a thought, bringing it into action. We are capable of adapting, like including with COVID, even those who were totally against online education have now adapted, and now we are continuing with it till such time that the time demands. So this is what sets in, or this is what makes us different and sets in that thought process that we are superior to the other animals. So one of the things which always interested every biologist who was studying human being, whether it's a anatomy of it or the physiology of it or the treatment part of it, was to study brain. Problem with studying brain, however, always has been that you cannot cut open and study the brain when the person is alive. And brain is too complex for us to just put 2 plus 2 together and understand what its function is. So over last decades or even centuries, the only way we could understand the functions of brain was either by conducting some experiments on some of the lower animals, including some of the primates, because they have their brains closest to us, and extrapolate that information on human brains and think that we also do exactly in the same way. It helped in certain places, but not always. Obviously, I believe, I at least hope, that we are slightly different from the chimpanzees. The second way we found out some of the details about brain was whenever a person had an injury and subsequently he presented with a set of symptoms. In postmortem, we could corroborate that this part of the brain was injured and therefore this particular thing happened. So that was another way we found out which part of the brain was doing what function. It's only now that we have functional MRI, probably we may come out with better understanding of brain functions, because human beings are comparatively quite a complex lot. Even our simple task of picking up a pen from table convey different meanings to different people. The force with which we pick it up, the way in which we pick it up, conveys whether a person is a happy person or an angry person trying to convey some other message. So there are layers to our activities, and we probably are still a long way away from understanding the exact function of every part of the brain. Some of the things we are now sure of, like for example, the motor areas, the sensory areas. But higher functions we are still learning. So an area of the brain which governs a particular function, that is what we call as functional areas. In this video, let us first learn about functional areas of the frontal lobe. It has most of the motor areas. So let us start with the primary motor area or primary motor cortex, otherwise labeled as M1. It's located in the precentral gyrus or area number 4, made up of agranular cortex, that is, it has got very few granular cells. Predominantly, it has got the pyramidal cells, including the largest pyramidal cells known as bed cells. Now, each of these functional areas will have some of the communicating fibers. One is it gets projection fibers input from some of the subcortical areas. It will be receiving association fibers from other cortical areas within the same hemisphere. It will be communicating with the contralateral hemisphere through the commissural fibers. The area will also be sending projection fibers to some of the subcortical areas as an output. So we will be learning about most of these connections. You need not remember each one of them, but at least you should remember those which will be important for understanding the functions. So for primary motor cortex, the projection fibers, which is marked in the green label, and throughout our series we will be marking it in the green arrow. The projection fibers will be arriving from ventral lateral nucleus and intralaminar nucleus of the thalamus. Now ventral lateral nucleus is receiving input from cerebellum. Intralaminar nucleus in this case will be receiving information from basal nuclei. Both these are giving the motor input, motor information. So that is why the information is reaching the motor cortex. Association information that is coming from the other areas in the same cortex, it comes from the sensory areas and other motor areas. It sends commissural fibers to the contralateral primary motor cortex, that is area number 4. And what is its output? The main output is the corticospinal tract and the corticonuclear tract. So this is the area which is involved in initiating finely controlled and fractionated movements. So the cerebral cortex primary motor area is the boss. That is what tells the contralateral half of the body to act. It initiates, especially in case of finely controlled movements, it is the one which dictates. It doesn't actually tell which muscle has to contract. It just says this activity has to be done. Now that information is carried through the corticospinal or corticonuclear fibers to the motor neurons, which are present either in the anterior horn of the spinal cord, so that will be through the corticospinal tract, or it will be present in some of the motor nuclei of the cranial nerves. So that there it will be reaching through the corticonuclear fibers. Now that is the main output from this primary motor cortex, which will then control the movements which will be elicited by those lower motor neurons. Within this primary motor cortex, different body parts are represented at different areas. Like I teach my students, like it is as though your body is hung on a clothesline at the level of knee. So that on one side we have leg and the foot, other side the body is upside down. Now just make it a little gory. Let's say that person has cut his head and he's holding it in his hands when he's hanging on upside down on the clothesline. So that clothesline is the superomedial margin. The leg and the foot will be on the medial surface of the precentral gyrus. The rest of the body lying upside down. So we have from above downwards the thigh, the pelvic region, the trunk upside down. Then we have got the shoulder, arm, forearm, and then we have hand, and in the hand further below that is the head region. Now here the whole body representation is of that of the contralateral side. Although some 10% neurons can be projecting to the ipsilateral side, these will be restricted to the trunk region. In addition to that, because the upper part is for the rest of the body, the fibers which will be starting from here will be projecting as corticospinal fibers. The lower 1/3, which is representing the head region, they will be projecting as corticonuclear fibers. If you notice the area here, it's not the size of the body part itself which will be having a proportionately large area of representation. Instead, it is that area which has got more fine or fractionated movements. So hand and the head region has a larger area of representation compared to the other parts of the body. Within this precentral gyrus, there is what is known as movement synergy. So here it's not that the biceps is represented or a triceps muscle is represented. Instead, it is all those muscles which will be involved in performing one function. They will be represented together, known as movement synergy. Also, within this precentral gyrus, there is what is known as motor plasticity. Let us say a person has amputation of his right-sided forearm region, or that is hand and forearm are lost. So there are neurons within the motor cortex which will be controlling the activity of forearm and hand. But once that part of the limb is lost, they will soon take over controlling the function of nearby area. So there is motor plasticity. Now coming to other motor areas, just in front of the primary motor area, we have premotor cortex, which is located in the area number 6. It extends through the superior, middle and inferior frontal gyrus. It's divided into two parts, premotor dorsal and premotor ventral area. Again, its information comes through ventrolateral nucleus of the thalamus as well as the intralaminar nucleus. Association fibers will be coming from various sensory and motor area, including it will also receive information from dorsolateral and ventrolateral prefrontal cortex. Now this part of the prefrontal cortex is the master macro planner. It will tell what needs to be done, motor activity. It makes a decision. It doesn't break it up into movement per se, but then yes, I need to go take a walk. That kind of a macro planning probably will be done by the prefrontal cortex, which is conveyed to the premotor cortex. So that information is also coming through the association fibers. Then of course commissure fibers to the contralateral motor area 4, premotor area 6 and the sensory association area 5. Premotor area also sends its output mainly as corticospinal tract fibers. So what's the function of premotor area? In fact, compared to motor area number 4, this is almost 6 times larger. It's involved in programming of the movement, specifically selecting direction and also postural fixation, but it is basically programming any movement. The dorsal part of it is involved in internally guided movement, and ventral part is involved in externally guided movement. Now what do we mean by internally guided and externally guided movement? Let us say I'm sitting at my desk and someone just throws a ball at me. So the incoming ball is the externally guided, it's an external factor. So now I stretch my hand to hold that. Now that's an externally guided movement. Now that I've got the ball in my hand, I decide what to do. Whether I want to put it in my drawer and forget about it, or want to throw it back to the person who threw it to me. So that action is an internally guided movement, in which case it will be the dorsal part of the premotor cortex which will be active. The third motor area is the supplementary motor cortex. It's present on the medial surface. It's located in the area 6 again, but on the medial aspect, as well as with the adjacent area number 8, which is in the medial frontal gyrus, and area number 24, which is in the cingulate cortex. Now, within this supplementary motor cortex, we have the leg area represented posteriorly and the face area represented anteriorly. Its connections again are from the various nuclei of the thalamus which are getting the motor input, that is ventral lateral and ventral anterior, along with intralaminar also from the medial dorsal. Association fibers, again it is connected to both motor area, primary motor area and the premotor area, to sensory areas, dorsolateral and ventrolateral prefrontal cortex, also the other prefrontal cortices on the medial surface and the inferior surface known as medial prefrontal cortex and orbitofrontal cortex. Commissure to the opposite side motor areas. Again, its output, main output is to the corticospinal tract fibers, but it also sends fibers, the output to the various other motor areas of the same side also. Now, what is the function of this supplementary motor area? Now, this is what is involved in motor planning. This is especially active in temporal organization of sequential movements, like any movement which requires a particular sequence. So, which part of the movement has to occur first, followed by next, which should be the next segment of movement. That temporal sequencing organizing is done by the supplementary motor area. It is also involved in motor memory. So let us say I learned how to cycle when I was a child. For next 30-40 years I have not cycled. Today if I sit back on the cycle, it may take me a few seconds to familiarize myself, but then I get back to cycling. So that is what is done by the because of the retrieval of motor memory stored in supplementary motor area. Anterior to this supplementary motor area, there is a small area which is involved in vocalization and speech production. Now, when we are talking about commissure fibers, whether it is from the primary motor cortex or from the premotor cortex or from the supplementary motor cortex, understand that whatever information or whatever activity is going on in one side of the limb is being transferred to the other side cortex. Now that's an interesting thing. Most of us are, let us say we are right-handed people, and I learned to write my alphabets using my right hand. God forbid, but if I have a fracture on the right side and so I'm under plaster, I can write alphabets using my left hand. Of course, my handwriting will never be the same, but I need not relearn how to write an alphabet with the left hand all over again. It already knows. So this information transfer will have occurred through the commissure fibers connecting the two opposite side hemispheres. There is also a secondary motor cortex known as MS2 that is located in the upper lip of the posterior ramus of lateral sulcus. So if you separate the two lips of the posterior ramus, the area adjacent to the primary motor cortex, that is area number 4. So just go on the undersurface along the upper lip of the posterior ramus. That is where we have the secondary motor cortex or MS2. So if you stimulate that area, that will again elicit movement on the contralateral half of the body. Therefore, it is called as secondary motor cortex. So now let us find out what happens if there is lesion to these various motor areas. Lesion to primary motor area will result in flaccid paralysis of contralateral side, decreased deep tendon reflexes. Please note these two are actually the element type of lesion features, but Babinski sign will be positive. In case of injury to the premotor area, we will be having decreased ability to perform skilled movements. Like the person will not be able to pick up and play his guitar, although he will be a guitar player earlier. And then there is problem in postural fixation of hip and shoulder. In case of injury to supplementary motor area, if the lesion is unilateral, then the person has what is known as akinesia. He's just not ready to get up and act, get up and do anything. Whereas in case the lesion is bilateral, not only he is unable to get up and initiate an action, but he's also got mutism, that is he's even unwilling to speak. Quite often this gets labeled as laziness, but this is also the feature of injury to supplementary motor area. When we have a combined lesion to all these motor areas, however, we get classical upper motor neuron type of features, that is spastic paralysis, exaggerated deep tendon reflexes, and Babinski sign will be positive. Apart from these motor areas, the frontal lobe also has frontal eye field, which is located in area 8 in the middle frontal gyrus. It also includes some of the adjacent parts of the adjacent area number 6 and 9. Again, coming to its input and output, its input, that is projection fibers, come from mediodorsal, ventral anterior, but mainly pulvinar part of the thalamus. But most importantly, its association fibers are coming from area number 17, 18, 19, which are the visual cortex. It also receives other input from the prefrontal cortex. Output is to premotor area and supplementary motor area, but most important output is to what is written here as PPRF, that is paramedian pontine reticular formation. Now it is that connection between the frontal eye field and PPRF, which is a nucleus within the pons adjacent to abducens nucleus, which governs its function. That is, this frontal eye field controls voluntary contralateral saccade. What do we mean by that? The left-sided frontal eye field will allow you to voluntarily look to the right. Now, looking to the right voluntarily involves right eye abduction and left eye adduction. Now, this is established by its connection with the PPRF. So, it sends information to the contralateral PPRF, which will then stimulate the abducens nucleus, which is just by its side. So, the right side, like let us say the information is going from the left side frontal eye field, it goes to the right side PPRF. That will stimulate the right-sided abducens nucleus. Therefore, the right eye will abduct because it will be supplying the lateral rectus muscle. And then through the medial longitudinal fasciculus, which we have discussed earlier, it will also connect with the left-sided oculomotor nucleus, especially that part which will be supplying the medial rectus. So the left eye now will adduct. So this is its function. So any lesion to frontal eye field the eyes will now deviate to the side of the lesion. That is because of the unopposed action of the contralateral frontal eye field. So if you find a person having one-sided hemiplegia and eyes deviating to the opposite side, like let's say a person presents with right-sided hemiplegia and eyes are looking to the left, that means there is involvement of cerebral hemisphere. So it is not a lesion at the level of internal capsule or anywhere in the brainstem, but this is most likely the lesion at the level of cerebral cortex, which involves motor area as well as the frontal eye field. And eyes look towards the side of lesion. The rest of the cortex now, which is in front of the motor areas as well as the frontal eye field, is what is labeled as prefrontal cortex. So it is the area present on the superolateral surface. Part of the area will also be found on the medial as well as in the inferior surface. Now on the superolateral surface, the area numbers 9 and 46 form the dorsolateral prefrontal cortex. Area numbered 45, 46, 47 as well as 12 on the undersurface together will be forming the ventrolateral prefrontal cortex. Similarly, on the medial surface, most of the medial frontal gyrus, including the frontal pole, and on the inferior surface, most of this orbitofrontal gyri, including the frontal pole, will form part of the prefrontal cortex. The part on the medial side is called as medial prefrontal cortex. Part on the inferior surface is called as orbitofrontal cortex. Coming to its various connections again, so we find that the input is from the pulvinar, mediodorsal and ventral anterior nuclei of the thalamus. Association fibers come from both superior and middle temporal gyri. These are the areas which will have, they are made up of association areas receiving input from various sensory modalities. Also, it will receive information from the auditory area and insula. Commissural fibers, of course, connect with the contralateral prefrontal cortex as well as with the inferior parietal cortex. Main output is to the premotor area and supplementary motor area in frontal eye field. Also will be communicating with the cingulate cortex and intralaminar nuclei of thalamus. So what is the function of this? This prefrontal cortex is the one which is involved in higher functions. So it helps in understanding of time and it allows one to predict consequences of one's own actions, or at least it is supposed to. It helps in appropriate expression of emotions. It's involved in calculation, thinking, and decision making. The dorsolateral prefrontal cortex helps in spatial processing and verbal working memory. Now, this working memory is important in any activity which involves learning. So, this is an area which is active during that time. In fact, the area number 9 is called as supervisory attention system. That is, whenever we are awake and alert, if we are doing any activity, whether we are talking, we are listening, we are seeing something, anything which catches our attention, this area number 9 becomes active. The ventrolateral prefrontal cortex is involved in mnemonic processing of objects. The medial prefrontal cortex is involved in visual and auditory association. The orbitofrontal cortex is actually the neocortical representative for the limbic system. That is, it is involved in emotions and memory, but it's at the cortex level, so it's at a higher level. The left-sided prefrontal cortex per se has an approach bias. That is, whenever we are engaged in any activity which involves communicating with the other person, like language-related activities or even approaching towards a person, the left-sided prefrontal cortex is active. That's why it is known as, it has an approach bias. The contrary is the right-sided prefrontal cortex. It has a withdraw bias. So whenever we are withdrawing from the people around us, maybe because of some fearful experience, whether it is real or imagined, the right-sided prefrontal cortex will be active. So let's find out what happens if there is lesion to the prefrontal cortex. Now, all of you just check out the story of Phineas Gage. That was the first indication of the activity or function of the prefrontal cortex. Now, this is a railway worker. He has his iron rod go through his left orbit and through the skull region. So it will damage the prefrontal cortex. The person goes on to live for another 12 years after the accident. But what people notice is sudden change in his personality. So go read up that story. It's an interesting one. In itself, it's a separate one video. So I'll not be dealing with it. So any injury to or any lesion of the prefrontal cortex will result in change in personality, lack of foresight, the person becomes distracted easily, abulia, that is lack of willpower. And with time, there may be change in the gait, that is he walks with shuffled gait which is got small steps, that's known as march-a-petit pas, and ask the patient to turn and he suddenly freezes. Now these two are actually signs of Parkinsonism, so often the case may be mistaken for Parkinsonism, but change in personality and all are very characteristic features of prefrontal cortex. Injury to the dorsolateral prefrontal cortex will result in slowing of mental processes, hypokinesia, that is reduced movements per se, apathy and indifference. Injury to orbitofrontal lesion, however, will result in hyperkinesia and increased drive of sex and hunger. Right-sided lesion to orbitofrontal cortex will result in compulsive laughter, whereas left-sided lesion may involve compulsive crying. However, if there is a unilateral focal lesion, a small area has a lesion because of lack of blood supply or anything, that will result in no obvious changes because it requires a larger area of the prefrontal cortex to be involved for any clinical presentation to be evident. So that's about the prefrontal cortex. Now, apart from these areas, in the dominant hemisphere, the areas numbered as 44 and 45 in the inferior frontal gyrus, that is the area which is located in the pars triangularis and pars opercularis, they are responsible for generating speech. They form what is known as Broca's motor speech area. We will be dealing with this area more in detail in our video on speech. Thank you very much. Hope you enjoyed this video. You can visit the site for other neuroanatomy videos.